Hello, everybody. My name's Steve Marks. I'm joined with Greg Suito, Matt Leal, and Alex Ally. We are the Capstone designers for the TACO cell pump controller. I'd like to thank our technical directors, Chris Kais, Daniel Hawkes, and Philip Mannon. So TACO is a manufacturer of pumps. Main use of these pumps is in agriculture. What the farmers do is they use the pumps to draw water up out of an aquifer or a well and uses them to irrigate their fields. It's not uncommon to see anywhere from a few up to hundreds of these pumps on a farm. They're spread over a very large area. So with that large area comes a great expenditure of manpower going from pump to pump, controlling and sensing. Currently, there's no other alternative for the farmers, no way to remotely control them. That brings us to our best anticipated outcome, which would be to create a wireless device that can sense the state of the pumps, control whether they're on or off, as well as communicate via a mobile app. Let me pass this to Greg to talk about the design a little more.
So here we have our block diagram, which gives a visual representation of our design. So as you can see, it's split up into a few main modules, first of which being power. So at the site of the pump, we will have a certain level of power available, which we'll need to take and convert down into levels that our microcontroller and sensors require in order to operate properly. Next we have our microcontroller, which is the brain of our device. Which is how each of the different components is going to be able to communicate and interact. Next we have our sensors, which is how we're going to monitor the pump in the different operating conditions, such as the flow rate, the water level, the temperature. Next we have communication, which is how we're going to be able to send data over a cellular network from our controller to a mobile app, where the user can monitor the different conditions of the pump, as well as control it. Which brings us into the motor control module, which is how the microcontroller is going to be able to interact directly with the pump, change the speed, turn it on and off, as well as monitor the state that it's in. And lastly, we have the mobile app, which is how the user is going to be able to monitor the pump from their phone and see all of the information that the pump is providing. All right, so creating this device has many implications, both for the company and the industry. First, this would be the first cellular pump controller device to be brought to market. There isn't currently a device out there that exists that provides this solution to this problem. So for the industry, it's going to make it a lot easier for farmers and miners to control and monitor their pump systems. Instead of having to go to each individual pump to monitor it and change it if they need it, they can just do it right from their phone, which reduces the overall time and resources needed to manage these large systems. And it also allows for early fault detection, because if something is going wrong with the pump, the sensors will detect that, and then we notify the user that their pump is not working correctly, and then they can more quickly either schedule maintenance or place an order for replacement parts to get their pump back up and running more quickly. And now I'm going to pass it to Matt.
Thank you, Greg. All right, I'm going to be talking about our technical accomplishments to date. We've been able to make significant progress on two of the major components of our project, that would be our pump controller and our mobile application. So first I'm going to talk about the mobile app. Here you can see a screenshot from our working prototype of our app. Here you can see all the values that are being recorded by our controller. And these values here are all updated on a live feed. In addition to the live monitoring, there will also be notifications built into the app. So say in the case that a water main bursts at the site, and so the app would send a push notification to the user so that they would know that there's a problem with the pump, and then they can then go into the app and switch this button right here to turn the pump off and stop potential flooding. Next, I'm going to talk about the pump controller. So the main design for this device is based around an Internet of Things type device. For our microcontroller, we decided to go with a BeagleBone Black, which you can see here at the bottom. This is a low-cost ARM-based microcontroller device, similar to a Raspberry Pi. We chose to go with this device because it offers a large number of GPIO inputs and outputs, of which most of these are being used for the LTE 4G communications. As you can see here with our SkyWire page and SkyWire modem. This we're using to achieve a two-way wireless communication between the pump and the AWS backend. And here we're using a 7.3-inch dipole LTE antenna just for testing. In the field, a large antenna is most likely going to need to be used. All right, I'm going to solve it out.
All right, so moving in forward into next semester, there's several things that we still need to finish for our application. First of which is going to be moving everything over to the AWS for the back end. This is going to be our databases as well as our functionality for communicating between the app and the controller. The plan is to be able to send the AWS a desired state for the controller from the app. The controller will then read that desired state and then make the necessary corrections. The mobile application, we have many more requirements to implement as far as the settings controls and user creation and authentication goes. Right now, we have the main mechanics of the app working, but just with generating test data. Nothing is pinging the API yet, because we still have to develop that. For the pump controller, we have to build in the system to record all the information, forward it back to AWS, and on AWS, we need to find a way to have it identify pumps that are malfunctioning in one way or another so that we can report that back to the user. As mentioned before, this is key in order to improve the product. So we'll bring this to the end. I just want to say a special thank you to our technical directors, Chris Kais, Philip Manning, and Daniel Jaquez, and of course, Dr. Sunak for providing us with this wonderful opportunity.
Okay.